Hello everyone. Just wanted to throw together a video kind of walking through cache. Uh, not really sure how long this is going to be. My goal is to sort of start from the very beginning and cover all of cache. So might be a little long, but I'll try to go through afterwards and find timestamps where I start to cover certain topics. So hopefully if you're only struggling on one particular concept, you can go ahead and just skip to that point. So the first thing that we pretty much need to discuss before getting into cache is just an overview of how the CPU generally interacts with the main memory. So in a computer, we're going to have the CPU and then the main memory. Right, and the main memory is going to be is your RAM in your typical computer, right? It's usually pretty big in comparison to a single bit. We're talking like 8 trillion or 8 billion bits or something like that. It's quite a bit of space. But the problem is that in order to be able to make RAM that big, it needs to be made with cheap technology, and you can't always get the best of all worlds. You're going to have to make some sacrifices in order to get cheaper bits. And the result is DRAM, dynamic RAM, which is a lot cheaper to build, but much slower and a lot harder to upkeep. But in any case, the main way that the CPU and the main memory interact is through a very, very basic interface. And this will vary between CPU and CPU and different computers. But the main thing is that the CPU will send an address to the main memory, possibly also some data, depending on if it's reading or writing. And then the main memory will just, if it's a write, it'll just write that information to the main memory. And if it's reading, then the main memory will return the data. And so, sometimes these two data buses will be the same bus, and it'll just go back and forth. And there's obviously tons of variety in modern CPUs about how this, in modern computers, on how exactly this works. But the main thing is the CPU just says, I want the data at this address, and then it gets it, right? It doesn't care how that happens. And that's pretty much that's pretty much where cache is going to come in, right? Main memory is slow, though it's big, and we can make it big because of the cheaper technology. But the cache we can make using a more expensive technology, but just make it smaller and inject it in between the CPU and the main memory. So we can instead have the CPU, then the cache, and then the main memory. Right, so then the CPU, well, it thinks that this is the main memory. Right, so all it's going to do is it's going to send memory addresses to read from. Well, with the cache, what we want it to do is just take that normal memory address, and then maybe it's in the cache because it was stored there previously. And if it's not, then it'll actually have to go to the main memory, right? But we want the interaction between the CPU and the main memory to be seamless, to not change from this, just the CPU asks for data at an address, and then it gets that data, or it writes to an address, and that just happens, right? The CPU interaction with the main memory is very, very basic. And so we want to make sure that doesn't break. So how can we do that? How can we create a smaller, just a cache? And in this case, a cache here just means that we're going to store values from the slower thing in the faster thing. And so if we're constantly using those values and updating them, we'll be essentially just working with the cache instead of with the main memory. And so we can do those interactions faster. So how can we design a cache so that it'll seamlessly interact, but still give an improvement in performance? And that's pretty much what discussing cache is all about. It's about figuring out a way to make it so that it seamlessly works. So for this, we're just going to assume that the CPU spits out byte addresses. No particular reasons for this. It wouldn't be that hard to modify it for word addressing, but just for the purposes of what I'll be covering, it's always going to be byte addressed, meaning every single address addresses a single byte in the memory, though you can usually typically read a word still. So let's say here we have the CPU on the left, then the cache here, and then the main memory. So we'll just make it relatively small as an example. So let's say our cache has just 4 spots. It can hold 4 pieces of information sort of temporarily between the CPU in order to improve performance, whatever that may be. And the main memory here, I'm just going to do 2 columns because that'll be a bit easier. So then we can have, location 0, 1, 2, and so on. And then 3, 4, 5, and so on. Or not 3, 4. Well, we would continue numbering down here, and then we might start back up here at like 16, 17, 18, or something like that. In any case, the main memory is going to be much larger, have many more addresses. So now the CPU might say, okay, give me the data at address 1. Okay, well, how would it be able to look to see if that value is in the cache, right? If we just stored data in the cache in some way, right, and didn't have anything keeping track of where that data came from, then we can't actually use a cache, right? We need some way to be able to say, okay, well, I'm trying to access address number 1. Where would that be in the cache? Or how could we actually check to see if it's in the cache? And that gets into how cache organizations work. And so to start, we'll take a look at what's known as direct mapping. And it's pretty much the most simple cache organization, and it's very basic and easy to implement. So for this, what we'll do is instead of just having a cache with boxes there, we'll still have 4 slots, but now each slot is going to be a little bit different. So we'll actually give what's known as an index to each of the slots, each of the locations in the cache. So we'll call this 0, 1, 2, or 3. So for the main memory, I'm just going to assume that there are 31 locations, or 32 locations from 0 to 31. Just because that'll make it easy. That means that our addresses can be represented with 5 bits. And keep in mind that increasing to more bits just essentially amounts to having a larger main memory or making a larger cache. The concepts and the work are identical no matter how many bits you're using. It's just bigger or smaller. So we have this, and then what we have inside of each of these is 2 things inside of these 2 locations. The first thing that we'll have is what's known as a tag, and here is actually going to be the cache line. Something to note about caches and how they work with the main memory, and even down to the CPU level. You're typically not accessing single words inside of the main memory. So if you're using a 32-bit computer, you're not going to say, okay, well, give me this 32-bit word or this 32-bit word, and that's the only thing it'll fetch. What will happen is it'll basically split up the main memory into these things known as lines, and it'll essentially just be some amount of bytes. I believe in modern computers, experimentally, you can find that 64 bytes typically is the most efficient. It's small enough that it's easy to do those transfers, but it's large enough that it contains enough information to give a performance increase. So we won't cover that. Obviously, our main memory here isn't 64 bytes, or it isn't even 64 bytes. It's only 32 bytes. But yeah, so we'll assume here just for now that a line is a single byte, just to make things simple, and we can get into some more complicated examples later. And so we'll assume here that our computer is just 8-bit. So even though everything is byte addressed, or actually, we'll go ahead and just say that one line is 2 bytes. So our computer is just 8 bits, meaning that just one of these bytes here would be enough to store in the register. But what will happen is that every time you want to read something from the main memory, in order to put in the cache, it'll actually read two locations. So it might be read these two or these two. Note that it wouldn't be able to read these two, and we'll get to why, but it'll always be two adjacents starting from 0. So 0 and 1 will be paired up, 2, 3, 4, 5, 6, 7, and so on. Those will be the ones that are actually paired together into a cache line. So I'll write this up here. So this will be our line, and then we have our tag here. So now suppose we access the address, let's say 12. So this right here is 12 in 5-bit binary. So we have only 4 locations in the cache, right? Which means we somehow need 2 bits of information from this here in order to decode which of these locations our cache is going to be in, our information might be in. So we'll say, okay, we're accessing address number 12. Now which one of these slots would that be in? And this is how direct mapping works, is we'll just say, okay, well, we'll look at some portion of the address. Maybe it's these 2 bits here. And we'll say, that's where it has to go. So this is 3 in binary, which means if this address right here was in the cache, it would have to be in this precise location, right? And that makes it very easy to implement, because you can just take that information, go directly to that location, and see if that's actually the data that you want. Whereas if you had to essentially go through and check every single one, algorithmically, you'd have to do that one at a time, and that would be inefficient. But in hardware, keep in mind, you can do things in parallel. So it would be possible to check to see if this particular data was in all locations simultaneously. But for the direct mapping, that's not how it works. It's just you take that information and go in. But now we have to somehow figure out which of the 2 bits is actually the ones that we need to use. And I would encourage that you think about why they come in this order. But the way that we're going to partition the address is first going to be the tag. So some amount of starting bits is going to be the tag. Then some next amount of bits is going to be the index. Then some amount of bits is going to be what's known as the word portion of the address. And this essentially allows you to address a word within a line. So in this case right here, we have 2 bytes, which means we're going to need some amount of information to address whether we're trying to access like byte 0 or byte 1 of this line. And then we have a byte portion, which in this case isn't going to really matter because our words are bytes. But this typically is the number of bits that you need to address a byte within a particular word. So what we need to do is, based off of the size of this main memory, the size of the cache, the fact that we're using a direct mapping, we need to figure out how big each of these portions are. And according to the information we have provided so far, we can figure out exactly what each of these values, each of the sizes of these portions of the address need to be in order for everything to work. So I always start with the index, and hopefully it'll be clear why. And it will become more clear as I talk about the other cache organizations, because to compute the size of the index portion of the address is the same for pretty much all of the cache organizations that I'll be covering. So for the index here, what we want to do is figure out how many indexes there are. In this case, in this problem, we know we've said that this cache right here has 4, right? So in order to address 4 things, we need, well, that's 2 to the power of 2 things. And so we can look at this exponent here to figure out how many bits that we need to represent that, right? If we have 4 things, then with 2 bits, we can do 0, 0, 0, 1, 1, 0, and 1, 1. And that's 4 unique ways to identify 4 different things. And so what we'll say is that the index portion is 2 bits, right? So that means, well, we don't know which 2 bits exactly, but we'll know once we fill out the rest of these. So then the word and the byte, these can be done independently usually, because it's almost strictly defined in whatever situation you're in. But here we can look at the byte portion, and this we want to see, okay, how many bytes are there per word? Well, here we're dealing with an 8-bit CPU, so one word is equal to 1 byte. So if we wanted to figure out how many bits we need to address a byte within a word, well, if we have one option, how many bits do we need? You might think 1 bit, but if you have 1 bit, you can represent 0, 1, which actually allows you to represent 2 things. So in reality, you don't need any information to address a single object, right? Because it's the only option. So this 1 here is 2 to the power of 0. So this byte portion is going to be 0 bits. And that makes sense, right? Because whatever word we end up at is a single byte. And so we'll know what word that is. We don't need to address a byte within that further. The word portion deals with how many words there are per line. Well, a word is a byte here. So we actually have that one line is 2 words, right? Which is 2 bytes. And so how many bits do we need to address 2 things? Well, 2 is 2 to the 1, so we need 1 bit, right? And then the tag we're just going to always define as being whatever's left over. Within the address, right, we'll use the index to figure out which of these locations in the cache it's going to be for the direct mapping. And then we'll use the tag, and that we'll store the tag for whatever address this data corresponds to here. And so all we need to do is we'll go look at the index, go to that index in the cache, and then look at the tag and compare it to the tag of the address that we're trying to access. And if those match, then we know that the data that's stored here is the data that we want from the main memory. So here, our address in total is 5 bits. This incorporates only 3 bits, so that means this tag needs to be 2 bits. And so we know that of this address, these 2 bits right here are the tag. These 2 bits are the index. And then this bit right here is the word portion of the address. So let's see here. Let's say at location 12, we have, I don't know, let's say the number 49 stored in there. I won't write it in binary because there's not really any use for it. And then we'll also have location 13. Let's say we're storing 42. So now let's go through the process of seeing what would happen if we accessed memory location 12. And keep in mind that, yeah, these are the different portions. 2, 2, 1, and then 0. So we're accessing location 12. So the first thing that we do is CPU is going to send that 12 to what it thinks is the memory. It doesn't necessarily know that there's cache there. Modern CPUs, it does, because the cache is typically on chip. But for the purposes of this, we'll just pretend as though the CPU doesn't know the cache is there, and it's just trying to access main memory. So it sends a 12. Okay, well 12 is this in binary. And so what we'll do is we'll look at the tag, the index portion, and that's a 2, right? So that means if the data associated with address 12 is in the cache, it has to be at index 2. And so now we would look at the tag, and we say, okay, well the tag here is 0, 1. Well, the tag here is, in reality, there would be something in the cache, but let's just assume it doesn't match. And so it'd say, oh, well, that kind of sucks. It's not in the cache. And so what it would do is it would actually then go to the main memory, go to memory location 12, and then it would take the whole line associated with that. And the line here is going to be these 2 bits, because it's just contiguous 2 bytes, and it always is going to essentially be associated to this, right? You'll chop off the word and byte portions, and then you'll go to whatever this address is with the rest of them set as 0. And so if we look here, this right here with this set as 0 is 12, and so we'll go to 12 and load in all of the bytes that are associated with a particular line. So we have the data 49 and 42. And so we'd sort of essentially have our 2 bytes here, 49 and 42, stored side by side. And that is something to note as well, is once we read the data from the main memory, it'll get written first to the cache. Now, that's not necessarily something that we have to do, but it is something that actually turns out to be beneficial. It goes based off of the concept of least recently used. So experimentally, if you actually run a whole bunch of programs, you'll find that most of the time, you're either going to access a memory address you've never accessed before, in which case you can't really predict it. In reality, in modern computers, there are branch prediction units that can actually do those sorts of, or not branch prediction, but memory prediction units that can actually predict what the next memory address is going to be. But for the most part, it's either going to be something you haven't accessed before, or it's going to be like it's ever before, or it's something that you're going to have accessed very recently. And so what we'll do is whenever we access something, we'll put it into the cache, because the probability is either we're going to use it again very soon, in which case we want it to be in the cache, or we're never going to use it again, in which case it's sort of a waste, but that chance that we'll use it again is high enough that it's actually worth doing. So we'll actually put it back in the cache. And so now in the tag, we'll say, oh, this is associated with memory location 12/13. And so we'll put the tag here. We'll say the tag now is 01. And actually, we can go ahead and rename these to 00, 01, 10, and then 11. And it might be a little bit weird to go by index then tag first, but again, all you want to think about how the memory is laid out and how switching these two would cause a difference in layout, but that's not super important. So we would do this, then we would say, okay, well now we want memory location 12, so we know that the data is stored here, and the word portion is 0, which means we'll get this one, right? So this would correspond to word 0 and word 1. So we would get this data and return it to the CPU, and it would get the data properly, right? Which is exactly what we wanted. And so let's look at a different address, right? I'm not going to worry about exactly what the data is, but let's say we're accessing address number 5 now. Right, so this is 5 in binary. Again, we have the tag is these 2 bits, index and byte. So now let's say the CPU is like, hey, I want to write something to location number 5. So let's say it's actually trying to write information here. Let's say it's trying to write the number 16 to location number 5. What it'll do is it'll basically say, okay, at location 5, write a 16. Okay, well, 5 is this. So it'll go to this tag here, which is actually the same. I'll go ahead and change it for this purpose. Let's say instead of 5, we're trying to access 8. So that would be 8. So this is the index, the tag, and the byte portion. So index is 0, 0. It would then try to compare the tag. It would see, oh crap, the tag doesn't match, right? We don't have a hit here. And so what it'll do is it'll actually first fetch the line from memory. So it would go to location 8 and 9, and then get whatever information's here, right? I don't really care too much about that for right now. And then it would actually bring it back into the cache. And so it would then match the tag. So we would put the tag here, and it would have the right data. Then the write would be performed to the cache. And essentially the way that the cache and the memory are going to interact is that it's always going to try to make sure that, well, eventually all the stuff from the cache gets written to the main memory. And in reality, you know, you have multiple cores, and multiple cores will actually typically communicate through the main memory or one of the higher levels of cache. So there's a whole lot of complicated stuff going on. But for simplicity's sake, essentially, eventually the stuff from the cache is going to get written to the main memory. So what's between these two is consistent. And so what would have happened here is 816, we would see, oh, wait, it's not in the cache. And so what it would do is it would actually go through and immediately write it to the main memory. And so now at location 8, we would have the value of 16. And then that data would get read back into the cache. Again, under the principle that we might use that immediately afterwards, because that's a common thing to happen. And so here we would have 16 in location 8, and then perhaps, you know, something in location 19. And then that data, you know, that would be the end of it, right? Because writing, we don't actually have to send anything back to the CPU. Okay, so just for one other address, let's say now we try to access address number 13, and 13 is going to be 01101. So this right here is going to be the tag, that's going to be the index. So now CPU sends over 13 and say, hey, I want the information at location 13. So what does it do? Well, it'll go ahead and go to the index 10 again, because that matches. And then it'll look at the tag, it sees 01, and it sees the tag here matches 01, which means it knows that this data is right here. And in fact, it is, because at location 13, we have the value of 42, and that's right there. So then we just look at this thing and know we want to read this word here. And so that's what we get returned. And we get returned 42. And we see that it never had to interact with the main memory. And that's saving time. And so that's pretty much what the direct map cache is you have an index that tells you where the data is going to be in the cache, if it is in the cache. And then you have this tag that you can use to actually determine whether or not it actually was in the cache. So the other, one of the other cache organizations is fully associative. And the way that fully associative works is now instead of having this index, what we're going to do is just make it so that we can store anything in the cache at any time. And in theory, this is the most efficient way to make a cache. However, it's far more expensive. It requires a lot more circuitry to get working. So again, we'll have our CPU. I won't worry about too much about the particular examples here. But we'd have our CPU. And the fully associative cache, I'm going to draw slightly differently. And it will become apparent why I draw it like this when I start talking about the last cache organization and how all three are related. But this is essentially how a fully associative cache is laid out. Right? We just have a whole bunch of tags and lines that, what was at each of the indices in the direct map cache. Now we just have a whole bunch of them on a single line here. And then we'd obviously have the main memory. I'll go ahead and just have a model of this down here. So again, we're just assuming this is big, however big the cache would be. It doesn't actually really matter for how fully associative works. But then we'd have a tag and then a line. Here, yeah. We have our tag and then a line. And these two are associated, right? These two correspond, right? This line, this cache line, is associated with this tag. And this tag is associated with this line and so on. And then we have tag and then a line. So now, with a fully associative cache, let's say we say, okay, well, give me address 12. And we're going to use the same 8-bit computer, one line equals 2 words, which is the same thing as 2 bytes, right? Because 8 bits. So each of these lines here is going to hold 2 bytes. So let's say, again, we access memory location 12. Well, now we don't have an index. We don't have an index portion, right? We're going to say that this data right here could be stored absolutely anywhere in this cache. And so if we look at the binary representation for 12, what we'd have is we still have to have this word portion, right? That's going to still be this 1 bit, but the rest, all of this information here is going to be the tag. And it'll allow us to essentially say, to just know whether or not this data is in the actual cache. And so we, let's say, try to access 12. It's not there, so we'd get it from the main memory. It would write back to the cache first. And so here we'd say, okay, well, the tag is 0110, and then the data is whatever it is. Then if we access location 13, well, now this would be a hit, right? So it would take the tag, it would compare it to all of the tags in this list. And keep in mind, this can be done in parallel because it's hardware. So it's not going to be checking one, then the next, then the next. You can check all of them simultaneously. And so we can see here that the tag matches, so it would just get the word out of this line. If we then access something like 14, that would maybe go over here. So let's say, well, no, let's not do 14, let's do 30. So 30 is going to be 11110. And so it would look for this in the cache. It would say, oh, maybe it's not there. And actually for this example, I'm going to go ahead and cut this cache off to just 2 locations. So it might do that. It says, oh, it's not there. It would, again, get it from the main memory and then put it into the cache. So it'd say, okay, well, there's something in this location, so I'll go ahead and put it here. So the tag would go here, and then whatever data would go here. But now, what happens if, let's say, we try to access memory location 0? Or just for some, we'll just say 5. So let's say we're trying to access location number 5. 5 in binary is that. So, well, it's obviously not in the cache, right? Because we'd look at the tag here and we'd say, oh, well, that doesn't match and that doesn't match. So we know this data isn't in the cache. So we get it from the main memory, but now we've run out of room, right? In reality, we probably have way more of these, but eventually we'd run out of room. So what do we replace, right? With the direct map, and that's actually something I didn't mention about the direct map. If you try to access something that would end up going to the same index, you just replace it. Because again, it's going to be the most recently accessed thing, and so that's what you want to put in the cache. So just sort of side note here, if we, let's say, have our cache here, and we access memory location 12, which is 01100, our tag would be this. If we then tried to access 5, which is this, we see that the indices matched, and so we'd access 12, and then at that location, at that index in the cache, we'd have the tag 01, and then the data for associated with address 12 and the line that 12 is in. Then we'd access 5, we'd say, we go to this index, we'd look at the tag, we see the tags don't match, so we'd go to the main memory and come back here and overwrite what's in here, and we'd say, okay, well, now we have the data associated with the tag 00 and whatever new data is here. So we'd have to replace it. And with the direct map, there is only one thing to replace, so we have to replace that. But with a fully associative, we have multiple things that we might need to replace. And so which one do we replace? And the question again comes to, what was the oldest thing in the cache? And in this case, we know, just sort of based off of what actually happened, that this is the oldest. But in hardware, we'd need some way to figure it out. And I can talk about that later, but for now, what's important is it just replaces the oldest thing, right? That's the thing that goes away. So in this case, we'd access this, we'd say, oh, it's not in the cache, we'd get it from the main memory, and then we'd replace this one here, 0 0 1 0 1, or that last one wouldn't be there. It would just be that with whatever data is in the line, right? Okay, so now let's say we access location 31. So 31 is just going to be 5 ones. So here we have a hit, right? So that means we'd access this one. We just return that data, don't have to interact with the main memory. And now let's say we access location 16, which is going to be that. So our tag is this. And so it'd look in here and say, okay, it's not in here, so it'd get it from the main memory. And now it has to replace something. Well, we just overwrote this one, but then we accessed this one. And because we accessed this one, we don't want to replace this one, right? We want to replace the thing that we least recently accessed, not necessarily least recently written, right? Because if we were going based off of what was the oldest thing that we wrote, it would be this. But the oldest thing that we accessed was this. In this case, there's only 2, so it's not really all that old. But the reality of it is, even if we had more, you always replace the thing that was least recently accessed. That's why it's least recently used, not least recently written. So yeah, this is pretty much how the fully associative cache works. You take the data from the main memory, and then it can go in any of these locations. You just have to figure out which one to put it in based off of what's the oldest thing. So on one hand, we have direct mapping, right? It's cheap to make, essentially, because that whole process can be done very, very easily, but not necessarily as efficient, because we might be just constantly replacing things in the cache, right? Not as efficient. Because, yeah, if we access something with a particular index and then access another location in memory with essentially that same index, it's going to have to go to in that same exact index in that same exact location as that other one. And so they'll constantly be swapping back, and you always have to get from the main memory, and that's not very efficient. Whereas with the fully associative, it's expensive, but as efficient as we might possibly want, right? If we are not getting as great efficiency as we want, we just make a bigger fully associative cache, and it's going to be better because it'll be able to store more things. So it's essentially the most efficient. Actually, I can go ahead and just call this least efficient. So, well, is there some way that we could combine the two concepts? And the answer is yes. And it comes in the form of what's known as a set associative cache. So, set associative cache, the first thing, the easy way to describe it is that you'll have multiple smaller fully associative caches that are accessed based off of an index. So we're essentially merging the concepts of direct mapping and fully associative to actually get these set associative caches. So here we can model the cache, and I'll make it a little bit bigger this time. So here we have our cache, and so we might have index 0 here. And so we're going back to the indices, and this is the same way that indices work with direct mapping. But now, inside of this location, instead of having just one tag in one line, we might have multiple. And for this, for instance here, let's say, with set associative, you have something known as the way. So we might say 4-way set associative or 8-way. Typically, it's a power of 2, but it's possible to do non-power of 2s as well. And that way right there essentially tells you how big the fully associative cache is at each location, at each index. And so a 4-way set associative means you have essentially a set size of 4. And so here we'd have 4 locations, which each have a tag and then a line, tag and a line, and so on, right? And then we'd have another index 1. With another exact copy of this, right? It would have a tag line, tag line, tag line. And so now the process for reading is just the combination of fully associative and direct mapping. The first thing that you do, so let's say we're accessing the address 12, and I'll keep everything the same size. So address number 12 would be that, and let's assume again that that is the index and that's the tag. So here we'd go to this index, which would be index 2, and then we'd compare it. Normally with direct mapping, we'd compare it to the only tag that's there. But with set associative, we're going to take the tag and compare it to all 4, at least in the 4-way case. We're going to compare this tag to all of the tags here and figure out whether or not it's in the cache. And that's that fully associative process. So this is why I drew the fully associative horizontally, is because you can sort of think of a fully associative cache as a set associative cache with a single index, right? It only is just this one massive row where anything can go. And direct mapping, we have that direct mapping is actually just a one-way set associative cache. And that's probably the easiest way to remember cache organizations, is if you can get the idea of how set associative caches work, well, then you know how both direct mapping and fully associative work, because they're sort of built into set associative caches, right? Because if we have a one-way set associative cache, then at each index, we only would have, one tag in line. That's a set size of 1, and so we only have one tag to compare, which is exactly just what a direct map cache is. And if we think, we can also think of fully associative as being sort of like n-way set associative. It's a little bit bizarre, but you can sort of, I like to think of it as sort of a spectrum. So we have sort of this ray here, right? And so we start at the beginning, we have one-way set associative, which is the same thing as direct mapping, right? Then we can sort of bump up and go to two-way set associative, and that's going to be a little bit more efficient because we're able to store two things at each index instead of just one. And then we can go to like four-way, eight-way, and we keep going, and then all the way at the end here, the absolute maximum is fully associative, right? As we keep making the set size larger, like let's say we fix the size of the cache to a certain number of bytes, well, we'd start off with direct mapping all the way over here, and then we can increase the set size, increase it, and once we get to the maximum possible set size, that's actually a fully associative cache, because essentially as you make the set size bigger, you're going to have less and less indices if you try to fix the size of the overall cache, and so eventually you just end up with every single cache line being on the same index, which is what fully associative caches are. And so we can go ahead and model that a little bit, model how set associative caches work. So again, let's take a look at, well, in this case, I'll look at the same sort of cache, but I'll make it a two-way set associative. So now we have two-way set associative. Again, one word being 1 byte, and one line being 2 words. And just again to note, all of these things are sort of defined, right? In a computer, these are fixed values, and so these equalities here might change based off of which system you're looking at. But with our two-way set associative cache, with again our 5-bit addresses, we'll go ahead and keep the tag being 2 bits, the index being 2 bits, word being 2 bits, and 1 bit, and the byte portion being 0 bits. So our cache here, it would go ahead and get split up into only 2 indices this time. Actually, no, yeah. We're actually going to change the index to 1 and the tag to 3 bits, and that'll become obvious why. So I'm actually keeping the set of the size of the cache fixed. So before, again, keep in mind we had the direct map cache, which had 4 locations in it, and each location stored 1 line, right? So in total, our cache could store 4 lines. Well, now if I'm going up to two-way set associative, then each index is going to store more, so I'm going to half the number of indexes. And so now we still have 4 lines, but we only have 2 indexes, 0 and 1, and so our index is only going to be 1 bit. So all right, let's see what happens. So again, we have the CPU all over here, and it's sending stuff over this way, and then we have the main memory over here. But we're really focusing on how the cache works. So again, I'll just use memory location 12 as an example. So now we have 0, 1, 1, 0, 0. And so here, again, want to look at how everything's split up. So the tag is going to be 3 bits, the index 1 bit, and the word 1 bit. So the first thing we're going to do is we're going to look at the index. That's index 0. So then we compare it to both of the tags that are in here. In this case, we'll just assume that the cache holds information that is completely irrelevant from when we're accessing, just for the purpose. Or you can just think of it as empty. So here we see, okay, well, nothing's in the cache, so that's a miss. So we'd get the information from main memory and then put it in here. And so we may put it in this first location, say, okay, that's the tag, and that's the corresponding data. Okay, now we can access a different location. Now let's try to access location number 5. You know, and as I had mentioned, that caused a conflict last time. So with 5, we have 0, 0, 1, 0, 1. And so this right here is the tag, index, and the word portion. So now we see, oh, well, it accesses the same exact index. So that's going to create an issue, right? Well, not actually, because even though the index is 0, we have another location. We have an entirely new thing. So we know, we look at 001, we look at the tag, and we say, okay, well, it doesn't match this one, doesn't match this one. So we get the data from the main memory and put it in the cache. So we put it over here and then set the tag right here. And so now we can store 12 and 5 at the same time. And really it would be a little bit different because we'd actually store 4 and 5 here and then 12 and 13 here, as I had talked about. But yeah, and so now let's say we go back to 12. Well, now if we go back to 12, again, 12 is this. So this would be our tag, index, and byte, or word portion. And so we'd go to this index here, index 0. We'd look at this tag, say, hey, it matches, so we have the data, and we can go ahead and return. And then if we for some reason our program was alternating between accessing memory location 12 and 5, 12 and 5, 12 and 5, 12 and 5, and just going back and forth like that, then we'd have no problem. The data would always be in the cache. With the direct map, we'd constantly be swapping. We'd say, okay, access 12, okay, put 12 in the cache. Then access 5, then replace 12 in the cache with 5. And then access 12, replace 5 within cache with 12. And you just keep going back and forth, and always having to access from main memory and keeping the cache intact, which means it would actually be slower than if you just didn't even have a cache at all. So having even a small two-way set associative, it's not all that much more expensive to build, but it's going to be much easier to actually work with. Additionally, with a two-way set associative cache, let's say you want to keep track of which one's older. If we call this like entry 0 in the set and this entry 1, well, then we can store a single bit of information here that just says, that keeps track of what's the oldest. So let's say we just access 0, right? We'd look at we'd basically look at the tags and say, okay, well, here it matched here, so that means we accessed location 0. And so what we can do is just say, well, bit one's the oldest. We can just keep a single bit, say, hey, one's the oldest. And then, well, we'd access 0, like we might access this one over here, and then it would be, oh, hey, now 0 is the oldest, right? You can't necessarily do that with multiple, but with 2, if you access 1, then the other one's the oldest. So it's actually really, really easy to keep track of that, and you can just do that with a single bit of information. So yeah, that's pretty much set associative. And again, keep in mind, direct map is one-way set associative, and fully associative is essentially the largest way set associative. So let's take a look at a couple of problems, because understanding how the cache is organized is the biggest hurdle. If you understand that, then solving some problems becomes a lot easier. And mainly what the problems turn out to be is, if you have a main memory of a certain size and you want a cache of a certain size, and you have a cache of a certain size with a certain organization, well, how does the address get split up? And if you understand how the cache is organized, it should be fairly simple to actually know how these get broken apart. So we'll go ahead and take a look at the problem. So let's say we have a CPU, some sort of computer, that has a 32-bit data bus. So the data that the CPU deals with is 32 bits, a 32-bit address bus, and then we have a cache, and we want that cache to be, let's say, 4 megabytes. Actually, we'll go a bit more realistic, something like 128 kilobytes. And we want the cache to be 4-way set associative. And we want our cache lines to be, let's say, 8 words. Okay, well, now how can we break apart the address, right? We know we have 32-bit addresses, meaning we know that our address is in total going to be 32 bits, and so we just need to break that apart. So the first thing to do, and the first thing that I always do, is just sort of mentally picture, or actually draw out, what this cache looks like, because that way we'll be able to actually keep track of what's going on. And we actually wanted to draw this quite big. But actually, before I get into that, one thing to do is write out all the information you know. At this point I have, but let's say this was given to you in a problem. Well, you'd actually want to physically write out the information in the simplest form that you can write it. So 32-bit data, what that tells us is that one word is equal to 2 to the power of 2 bytes. I've done a lot of conversion there, but again, so 32 bits is 4 bytes. Just divided by 8, you get 4 bytes, and then 4 is 2 to the power of 2. And I write it in power of 2 because, as you remember from that one example with the direct map cache, knowing that exponent is how you know how many bits you need. So writing a lot of these as 2 to the power of something is going to help. And at least for the purposes of 3181, we're probably always going to be given examples that are powers of 2 to make it simple. So, yeah, so we have one word is 2 to the power of 2 bytes. We know here that one line is 2 to the power of 3 words. And that's almost it. We also know that one set is equal to 4 lines because we have a 4-way set associative cache, or 2 to the power of 2 lines. And notice how I'm writing this, right? We can sort of convert from bytes to words, words to lines, lines to sets. And then also what we have is that we have, at every single index, we have one set. Now, this is always true, right? No matter whether you're dealing with direct mapped, set associative, or fully associative, each index is going to precisely have one set. Whatever size that set is, right? If you have a direct mapping, then that set is a single, is going to be a single line, but it's still a set. It's still just one-way set associative. When you're dealing with fully associative, you still have one index, but keep in mind that there is no need to actually you don't need any information to address one thing, right? If I have one object and I say, okay, how much information do you need to know to choose this object? You don't need any because it's the only object, right? Whatever you choose has to be this one. So if there's, in a fully associative, you have one index, which means you need no information. But that index, at that index, it's still just one set. It's one really, really big set, but it's still one set. So this is always true. And these pieces of information here will be given. So these will be given in some form. They might not necessarily be straight given to you, but those are the sorts of things that you should be able to compute given the information that you have. But this is always true. And that's important to know. So let's go ahead and draw out the cache. Also, I suppose we should probably actually figure out the size of the cache in power of 2, again, because that's going to make some of the math a lot easier. So we have that one cache. And, you know, it seems kind of dumb to say one cache, but again, these are all units, and we're just figuring out how to convert between units. And if we can do that completely freely, then we can solve the problem with no issue. So one cache here is 128. That's 2 to the power of 7. And then kilo is 2 to the power of 10. Just a small note here. K is going to be 2 to the power of 10. M is 2 to the power of 20. G is 2 to the power of 30. T is 2 to the power of 40, right? So kilo, mega, giga, tera, and then you'd have peta. And it just keeps, the power of 10 just, the exponent just keeps increasing by 10. So 2 to the power of 7 times 2 to the power of 10 for that kilo bytes, which is just 2 to the power of 17 bytes. All right, so now that all that data is converted, now I would go ahead and actually draw out a model of the cache. So we'll start here and we'll say, okay, well, we have potentially multiple indices. In theory, it's possible that, you know, a 4-way set associative cache will only have one index if it's small enough, but this is going to be large, so probably has multiple indices. We don't really know how many there are, at least not from what's given in the problem. That goes back to what I was saying. I like to start with computing the index. In that one problem, it was very easy because we just had to find it to be 4. And sometimes it will. Sometimes in a problem, it'll just be given how many indices that you want, and you'd have to figure out some of the other values. But for this, we don't actually know how many indices there are, and that's what we need to figure out. But we do know that at every index, right, because we have one set, right? So at every index, we have a set. And in every set, we have 4 lines. And this is, again, because our set size is 4, right? Because we have 4-way set associative. And then keep in mind here, we'd have, our tag, and then the line, and then a tag, and then a line, right? That'd be for all 4 of these, right? Within each line here, and I'll just sort of blow this up because it's pretty small. So one of these is actually going to be subdivided into 8 words. So I'll go ahead and quickly subdivide that. Yeah, so each of these would be a word, a word, a word, a word, a word, right? Because we have one line is 8 words. And then each of these words here would be further subdivided into bytes. And here we have that one word is 4 bytes. So one of these words here would end up mapping to 4 bytes. And this is probably a good time to sort of take a quick break and talk about sort of this multiple levels of addressing. This is something that you came across looking at memory, and it's also something that happens in cache. And what it is that you'll take some large address, right? Doesn't really matter how many bits, and then you'll say, okay, well, I'll use these top bits maybe to address it within something, and then I'll use the next set of bits to address something else, and the next bit of the address to address something else, right? With a cache, you're going to use the index to address with which of these sorts of rows that you're in. Then you have the sort of weird thing that if the tag matches one of these, but then within that you have a single line. Well, then you can use the word portion of the address to address a word within a line. Then you can use the byte portion to address a byte within a word. And so we're, again, sort of using this multiple tiers of addressing to make our lives a little bit simpler. Rather than having to figure out how to deal with this whole address, we can break it apart and just take smaller steps. Sort of what you can think of about that as is sort of like a library or something, maybe like a hyper-organized library or some sort of document store somewhere, right? You walk in and the building has multiple floors, right? And then on each floor there's multiple rooms. In each room there's multiple sort of just rows. And in each row there's multiple filing cabinets. And in each filing cabinet there's multiple drawers. And in each drawer there's multiple files. That I've just described, I don't know, like 7 or 8 different levels. Right? Trying to figure out how to get through that, right? Let's say you want document number 4758B. I don't know if it's given in hex or something, right? How would you be able to find where that is? Well, if you break it apart, maybe that 4 tells you, oh, it's on the 4th floor, right? 6 tells you it's in room, I don't know, 46, maybe it's the 6th room on the 4th floor. And then you look at the next thing that says, oh, well, it's in the 3rd row. And then in the 3rd row, you can look again and if you do that, well, then finding a document actually becomes very, very easy. You can break it apart at a whole bunch of different levels and basically take the addressing one step at a time rather than having to do all of it at the same time, right? If you just had to look up in a directory that said, hey, this file is in this location, well, it would be difficult to go through and find all the files you need. But if all the files are organized very specifically and you can just based off of the ID, know exactly where it would be, that makes your life a lot simpler. But all right, we know how the cache is organized here. So now we can go ahead and try to figure out what the tag, index, word, and byte portions are. And again, we'll start with the index. So for the index, we need to know how many indices there are, right? Because the index portion, however many bits this is going to correspond directly to the number of bits that we need to address every single index. And so we need to know the number of indices. Well, with our cache here, we know that the cache in total is 2 to the power of 17 bytes. So how can we figure out the number of indices? Well, if we somehow knew how many bytes there were in a single line, well, then we can just go back to elementary school mathematics, and we know that the area of a rectangle is equal to the width times the height. And so if this is our area here, and we can figure out our width, which, because we know how the cache is organized and all of this information here, we can figure out what the width of the cache is. Then we can just divide to get the height, right? The height is just going to be the area divided by the width. And so we can go ahead and figure that out. So our area, again, is just the number of bytes in the cache. It's just 2 to the 17 bytes. Our width here, well, our width, what we want is essentially the number of bytes at a single index. So essentially we want some number of bytes per index. And so now we got to go back a little bit further in grade school, and maybe elementary or early high school, and look at unit conversions, back in sort of science. So we can start here by saying, well, we know we want something, we want bytes per index. So we want to start with something that's per index, right? Well, we have this always true thing. We always have that one set is equal to one index, right? One index has one set. So we have one set per index. All right, well, we want bytes per index. So can we somehow translate set to something else? Well, here, right, we know how to translate index to set, then set to lines, lines to words, and words to bytes. Well, that's exactly what we want. We want bytes per index. So if we do one set per index times 2 to the power of 2 lines per set, well, now these sets cancel out. Then we have 2 to the power of 3 words per line. Right, now these lines cancel out. And then we finally have 2 to the power of 2 bytes per word. The word cancels out, and now we can just multiply these units together and we get a unit of bytes per index. And so this will be 2 to the power of 2 to the power of 3 to the power of 2. So we just add the exponents here. That's 2 to the power of 7 bytes per index. All right, well, that tells us our width. Our width is 2 to the power of 7 bytes per index. And so our height here is just going to be area divided by width. And so our area is 2 to the power of 17 bytes. Our width is 2 to the power of 7 bytes per index. So here we take this, and again, just keeping track of early mathematics, right? When you have a fraction in the denominator, you flip it and you can just multiply it. So this right here is just 2 to the 17 bytes. 2 to the 17 bytes divided by 2 to the power of 7. And then here we can just multiply by the reciprocal index per bytes. So these bytes cancel out. And here we'd get 17 minus 7. So we get 2 to the power of 10 indexes. Right? So this tells us that our height, the number of indices we have, is 2 to the power of 10. Right? And if we have 2 to the power of 10 indexes, then our index portion is just going to be 10. And then figuring out the word the rest is going to be very, very easy. So the word portion is just how many bits do we need to address a word within a line. Not to be confused with the byte portion, right? That's something that you want to be very careful about. The word portion is talking about addressing a word within a line. So here we have 2 to the power of 3 words per line. So our word portion is going to be 3 bits. Then we have the byte portion. We have 2 to the power of 2 bytes per word. And so our byte portion is going to be 2, right? Just look at the exponent. Then, well, we have the index is 10. The word is 3. Byte is 2. So this is 15 in total. geez, 15 in total. And then the tag is going to be whatever's left. And we know here that our address is 32 bits. So this all needs to add up to 32. So 32 minus 15 is 17. And so the tag is 17. And that now you figure it out how the address needs to be split up so that it actually can be processed in the cache. Right, a lot of information, but as long as you keep in mind what it looks like and you're just keeping track of your units, everything should work out. So let's go ahead and take a look at a different system. Let's look at, let's say now, a direct map cache. So now let's say now our CPU has 16-bit data and we'll say 24-bit address. And so if I was reading this problem, I would sort of start jotting down some notes. So I'm assuming that what's up here in this corner is just the problem statement, and then everything else is going to be my own notes or thoughts as I'm going. So 16-bit data, that tells me immediately that one word is 2 bytes, or 2 to the power of 1 bytes. Again, which is equal to 16 bits. Right? So that tells me that. Then I have the next piece of information here, that our address is 24 bits. I don't really need to write that down, but that is something important. It also might be possible, it just tells you how big the memory is in bytes. Well, if we, again, assume that we're doing byte addressing, well, we'll have an individual address for every single byte in the main memory, and so we can easily compute how many addresses we have, or how big the address has to be. Then we have our cache. Let's assume here that it is, let's say, one of the smaller caches, so maybe only 64 kilobytes. It'll be direct map. And we'll say a line size of 16 words. Or actually, I'll just go ahead and use the 64 bytes. So one line is 64 bytes. Okay, so we have one word is 2 bytes. So now how many lines are there per word? Well, we have one line is 64 bytes. That doesn't tell us how much it is in words, so we just need to figure that out, right? If we have 64 bytes per line times one line per 2 to the power of 1, or sorry, one word per 2 to the power of 1 bytes. Right, now we can get word per line. So 64 is 2 to the power of 6. So 2 to the power of 6 minus 1. We get that there are 2 to the power of 5 words per line. Again, just units for everything. So one line is 64 bytes, which is just 2 to the power of 5 words. Okay, well, now how many lines do we have per set? Well, we have direct map, which is the same thing as one-way set associative, right? And so if you just know that, well, then we know that one set is just one line, because we only have one line per set. And then, as usual, one index equals one set. So, yeah, and then we also want to note down that one cache is 64 kilobytes, so 64 is 2 to the power of 6. Kilo is 2 to the power of 10 bytes, so we have 2 to the power of 16 bytes. And I believe that's all the information that we need. So now we can go ahead and, again, make a model of what the cache looks like. And this doesn't necessarily need to always be drawn out, but I would highly recommend that you at least think of what it looks like. At least just mentally picture what this looks like, so that you can actually get an idea of how the units are done. So here we have a direct map. We will have some indices. So here we will have a tag and a line, and we only have one because again we're dealing with one-way set associative, which is the same thing as direct map. We have a tag and a line. So index 0, 1, and then this would continue. We don't know how many, but we'll assume there's probably quite a bit because it is 64 kilobytes. All right, so now again, we want to figure out the tag, index, word, and byte portions. All right. So again, we can go ahead and just fill out the word and the byte to make it simple. So the word is the number of bits we need to address a word within a line. There's 2 to the 5 words per line, so we need 5 bits. The byte portion is the number of bits we need to address a byte within a word. There's 2 to the power of 1 bytes per word, so we need 1 bit of information for the byte portion. Now for the index, well, we have again our area of the cache is 2 to the power of 16 bytes. Again, that's just the number of bytes in the cache. Our width is going to be, well, we have 1 set per index times 1 line per set times 2 to the power of 5 words per line times 2 to the power of 1 bytes per word. Right, so again, set cancels out with set, line with line, words with word, and we just get bytes per index, and so we will get ultimately 2 to the power of 6 bytes per index. And then our height is just area divided by width, which is 2 to the power of 16 divided by 2 to the power of 6. Again, the units would matter here, but we know that it cancels out to indexes. So we get 2 to the power of 16 divided by 2 to the power of 6, which is just 2 to the power of 10. Again, just subtract the exponents, right? We can do, if with the exponents here, instead of having to do multiplication and division, we can just use addition and subtraction. So having everything as powers of 2 definitely makes a lot of the math easier, especially when you're doing this by hand. So we get 2 to the power of 10 indexes, or indices. You know, both of those terms are technically correct. So we have 2 to the power of 10 indices, which means we need 10 bits for the index. And our total address is 24 bits. So here we have 10 plus 5 plus 1, that's 16 bits. And so we need 8 more. So our tag is going to be 8 bits. And there you go. We'd figured everything out. So one last example I do want to give is a fully associative cache, which is probably the easiest of these options of all the different organizations to solve this for. And it'll become clear why. So we have our CPU. Let's say now we have 64 bits of data. And also a 64-bit address. Or, well, actually, we'll go to 48 bits. Then we have our cache. And, you know, fully associative caches are expensive. So let's just say this one is just 8 kilobytes. Again, fully associative. And we'll say 64 bytes per line. You know, same example, real world example. So again, just figure out all of our different values. So we have, I'm reading this problem and I start, okay, well, we have 64-bit data. So I know one word is 64 bits. 64 divided by 8 is 8. So we have 2 to the power of 3 bytes. Then we have, well, one line is equal to how many words? Well, we have 64 bytes per line. 64 is 2 to the power of 6. So that means, and each 2 to the power of 3 bytes is going to be one word. So that means we have 2 to the power of 3 words, right? If we just multiply these out, then we get 2 to the power of 6, which is the number of bytes per line. Then we have one set is equal to some amount of lines. We're not actually really sure, but it includes basically all of the lines. And then we also have that one index. And you might think this is a problem, but we'll see how it isn't, right? So, and then again, just convert our cache. So we have one cache is just 2 to the power of 3 for 8, 2 to the power of 10 for k, so that's 13 bytes. So now our cache, if you remember, the way that I drew out the fully associative was sort of as this really long, just single set. And that's how you want to think about it. And we have index 0 and no other indices, right? There is no index 1, index 2, or anything like that, right? So although we have a whole bunch of lines in a single set, and we're not necessarily sure, we could compute it because we know all of this information. But here we're just assuming we don't have any idea. And so we want to compute the tag, index, word, and byte portions. So how do we go ahead and compute the index when we don't know this information, right? Because normally we work up and essentially use all of these to figure out the number of bytes per index, but we don't know what's at this step. However, don't always get bogged down in first computing the width. Sometimes you just know how many indices there are. And with a fully associative, there's always only one index, right? Because every single line in the cache is stored in the same set. So our number of indices with fully associative is always 1. And again, 1 is 2 to the power of 0, and so we need 0 bits. And so the index is going to be 0, always for fully associative. Because of that, it's typically omitted. It's typically not actually included if ever you're sort of trying to figure these out. And also, occasionally, some texts will call this the address portion of the address rather than the tag, because it's mostly the whole address, right? The word and the byte portion are somewhat negligible. They're going to be rather small, and so this is pretty much all of the address. So instead of calling it the tag, they might call it the address, but you can just think of it as the tag. It's just whatever's left over, and it's used to identify if it's actually properly in the cache. So yeah, our index portion was 0. So now we'll want to look at the word portion. So we see that there's 2 to the power of 3 words per line. And so word portion is going to be 3. Then we have 2 to the power of 3 bytes per word. So our byte portion is going to be 3. And then the rest of it is in the tag, right? We didn't have to, we know the index is 0. And so we just put the rest of it in the tag. So this is 6. So 48 minus 6 is 42. And we're done. The tag is going to be 42 bits. Quite a bit, but it's natural considering that it's fully associative and that we have a fairly large address. So that's pretty much all I had to cover. I'm going to make another video about the reference matrices, if that's something that you're worried about. From the perspective of how a cache works, with the sets we're always going to be using LRU. There are other techniques that you can use, but just for our purposes, that's the only one that you need to worry about. But the reference matrices are a way to implement LRU, and it's not necessary. It doesn't have anything to do with how LRU works. Again, LRU is replace the oldest thing. That's the oldest thing that you've accessed, the thing that you've least recently accessed. That's why it's called least recently used. So I'll make another video just kind of walking through that, kind of walking through some examples. But yeah, hope you learned something new.